believe we have finished this theorem, right? Is that correct? Yeah. Okay. So this is the basic beginning. So f is an analytical function on an opposite, and the gamma is across the path. And in omega means that the range of the cross path is contained in the open set omega. And then if the derivative, because we know it's analytic, so by definition, f has derivative at every point in the open set. So the derivative is a function, right? So the derivative, so if derivative is continuous on the open set, then when we do the line integral, because we among a cross path, so sometimes we use this notation to integrate. It is a line integral over a cross path. And the integrand is the derivative of the analytic function f, right? And so this line integral is equal to 0. Okay. So this is quite a general theorem. So now we present the first version of Cauchy's integral theorem. Right? For a triangle. Right? So first of all, omega is an open set. Okay. The second thing is that P, a point in the open state. F is a complex function which is continuous on the whole open set. And differentiable okay. So it's very interesting condition. F is continuous on omega, but it is differentiable only on omega, but puncture the point P. Okay, so f has derivative at every point in the open set, except P point P. Okay, because here P is assumed to be a point in the open set. Fourth thing, delta a closed triangle. Omega. Okay? So it is a closed triangle. Omega. So the situation possibly. So this is omega, and we have P here. Okay. And we have, for example, possibly we have a triangle. So this is the triangle. So a triangle consists of 3 line segments. Okay, 3 edges. Okay, 3 edges. Then Okay. So the boundary of fz dz is equal to 0. So the triangle is here. Okay. So we have this triangle. Do you highlight this one? Okay. So the whole triangle, the cross triangle, including the boundary, okay, is in omega. Okay. And so along the boundary of the triangle, so this is a line integral, and the boundary of a triangle is a cross path, right? It's cross path, right? And either direction, okay, you can orient it clockwise or counterclockwise, okay, counterclockwise or clockwise, that's fine, right? By the way, because the value of the line integral is equal to 0. So this is the first version of Cauchy's integral theorem for triangle here. So just remember the situation. The point P could be outside of the triangle or inside of the triangle. That's fine. Okay. No matter which kind of situation, that the conclusion will be the same. Okay. Will be the same. So once again, I have to emphasize the complex function f is continuous on the whole open set omega, and it is differentiable, means that it has derivative at every point in the omega except p. Okay. So but remember at point p, f is continuous. Okay, it's continuous, but we may not have derivative at p. And the triangle, the chord triangle, including the boundary, is in the open set omega. Okay, so in the open set omega, then the line integral along the boundary of the triangle should be 0. Okay, so this is the first step. Any questions? Right. Okay. Because the proof extends to 2 pages, so it's too long, and I can't explain this proof here. Fortunately, I gave you the supplements already, right? So please take your time to see the proof, okay? And so now we will state the second version of Cauchy's theorem, Cauchy's integral theorem. This time in a convex open set. All right. So again, omega is an open set, an open but also convex. Say it. Convex open set. The second, P a point in this convex open set, that means f is continuous on omega and differentiable, okay, omega, but excluding the point P. Right. Then there exists an f. Okay. I don't know if I have. Okay. I need a notation. Okay. All right. A notation here. So let omega be an open subset of C. Now we use the notation H omega defined to be the set of all complex or analytic or complex function functions on omega, which are analytic on omega. Okay. And H actually refers to holomorphic. Okay. Holomorphic. Because analytic function sometimes called holomorphic functions, so that's why people use H. Okay. So analytic function. Analytic function is referred to the holomorphic function. Okay, it's just a terminology that people use holomorphic function to say analytic functions. Actually, they are the same thing. And that's why we have the H, the capital H, right? So H of omega makes all analytic function defined on an open set omega. Okay. All right. So wow. All right. All right. With F, which is continuous on an open and convex set. It's very important, convex, okay? And F is differentiable on the open convex set, except a point P, okay, in omega. Under these conditions, there exists an holomorphic function, okay, or analytic function on omega. So here that the capital F has derivative at every point in the open set omega, including the point P. Okay, so there exists an F, okay, which is holomorphic or analytical, such that the F prime, F actually is the derivative. Okay? We have that. And of course, for every closed x gamma in omega. Right, so the difference is that if the open set omega is convex, convex means that convex means that any 2 points you can connect them by a segment, and the whole segment will be contained in the set. So it's called convex, right? So this is a convex set, but this one is not convex because if we connect them by a 9 segment, this part is outside of the set. Okay, so this is a convex set. All right, a non-convex set. All right, so this one is not convex, but this is convex. Okay, so they are different. They are different. All right, so the difference between B and C is that for here, omega is just an open set, not necessarily convex. Okay, not necessarily convex. Okay, and the F is continuous on the open set and differentiable on the open set, except the point P, some point. Okay. And then we won't have this formula, means that over some cross path, the line integral go to 0. But for this case, all right, we just consider only the boundary of the triangle. Okay, boundary of the triangle here. Okay, specifically. But for here, if we have convex open set, we have the conclusion here that this is true for any closed path. Of course, the cross path including the boundary of triangle. Okay, but here this is more general. Okay, so this is true, right? For every cross path. In addition, actually the function f is the derivative of a holomorphic function on omega. Okay, so capital F is differentiable at every point of a convex open set. Okay, so we have that. Right, so we just have one more stronger condition. Right, we have a nice property, right? We have more nice property compared with that. Okay, of course, that's a theorem. This theorem is established from the previous theorem. Okay. Okay. Now, recall a domain, okay, a domain D in the complex plane is non-empty, open, connected subset of C. Okay? So the important thing is that it's open and it's connected. And I define connected state is that you have, if you have two points here, then maybe you have some holes here. Okay. Now you will be able to connect them by chain of segments. Okay, by chain of segment. So you have that. So this is a domain, even though it has hole here. Okay. So this is the domain. Alright. Now, suppose that together, and you have point here and point here. You can't find any chain of line segment to connect them. So this is open, but it's connected because it has two components. Okay, so this is the domain, but this one is open but disconnected. Right. Right. So a domain actually is defined to be an open connected subset. And a fact, I think I just stop here. Any open set, any open subset U or okay of C, right? Consists of countably many disjoint domains. So basically, any open set consists of many different disjoint domains. So any open set can be decomposed into domains. Okay, and the number of such domains is countably many. It's finite number, or if it's infinite, then you can count. So it's countably infinite. Like the set of all positive integers, right? Because the set of all positive can be counted. But the set of real number is uncountable. You can count, right? You cannot count the set of real numbers. Okay, so open set, so you can regard any open set in the complex plane consists of countably many disjoint domains. So domains like this one, you have that. Okay, now a simple closed path. Alright, it's a closed path. Okay, whose range gamma star does not intersect or touch itself. Okay, so a simple path like the boundary of a square. Okay, so this is simple. A circle, a triangle, boundary of a triangle. So they are all simple closed paths. Okay, so they are simple. but a figure of 8, okay, and then 8 over like this one, they are non-simple cross passes. So so cross path can be classified into simple or non-simple. Okay. So you can see they are simple, right? No intersections, no touching. So this is a simple cross passes. But for that, you have crossing, you have touching and crossing here. So this is they are non-simple cross passes. Okay, so now we define a simply connected domain. Domain in C is a domain such that every simple cross passes in D. So for every simple cross pass in D, enclosed or encloses only points in D. Right. So, for example, a disk. Okay, a disk. A rectangle. They are simply connected domain. Okay, they are simply connected domains. Because in here, if you have a simple, so the gamma is simple, right? Simple. It encloses only points, right? Points in the whole domain, or here. But if you have entire point, okay, or even you set a point without the center. Okay, so without the center, they are multiply connected multiply connected domain is a domain which is not simply connected. Okay, so we call multiply connected. Okay. And the reason is here, we have right? So this is a simple closed path. But the simple closed path enclosed point which is not in the domain, because we have a hole here, right? So we have a hole here. And the same for this gamma, which is simple. Right? For this simple closed path, it encloses the center, but the center is not in the domain. Okay, so this one and this one, they are multiply connected. Okay, and you can say a bounded domain. For example, all these are bounded domain because they are bounded, right? So a bounded domain B is called B4 connected. If its boundary consists of P closed connected sets without common point. Okay? So, for example, a bounded, this is a bounded, okay, domain. We have there is a hole here, and we have a point related, and then we have a cut here. Okay. A cut, right? So all this and some people cut this piece of region extensively. Now, so this is, of course, this is not simply connected, but it's a domain. Okay, it's a domain, but it's not simply connected. Okay, so it's multiply connected. Now, how many fold by this definition? How many fold? Well, we look at the boundary, okay? So, what is the boundary of this domain? Well, here, of course, here is one boundary, the second boundary, the third boundary, and the fourth boundary. So it's fourfold. Okay? So you can see that? Because it's a closed and what? And a connected set without common point. So this is a fourfold domain. Okay, it's a fourfold domain like this one. Okay. Okay, so now the next theorem, which is presented in the textbook, Cauchy's integral theorem. In simply connected domain. Right. So now, a simply connected domain. First, D, it is a simply connected domain. Okay. Second, E, a point in this domain. So things F continuous on D, okay, and differentiable on D that is coding point P. Another way to state this statement is saying that F is in, okay, F is holomorphic in this open set because the domain excluding a point in it is still an open set. Okay, so either you say this or you say this one. Then we have zero for every simple closed path. All right, so you have to compare the theorem with the previous one. We have a Cauchy integral theorem in an open convex set. Open convex set is a special kind of simply connected domain. Okay, so open convex. So we actually the theorem for the geometry of the defining set D, we generalize, right? We consider bigger class of open set, right? Because simply connected domain is a bigger class than convex open set. Okay. And we have the same second and third condition. Now, we have this nice formula. We have this nice formula, right? But for what? Only for simply, for any simple closed path. Okay, for the simple closed path. And then you can see one thing missing, right? The Cauchy integral theorem for convex open set has one additional property. What is that? It has antiderivative. Remember, if D is a convex open set, we have an F, right? Such that F is equal to, right? So we have an antiderivative function, right? F is called the antiderivative of F because the derivative of F is equal to the derivative of capital F is the little f. Okay, but this is true only for what? When D is a convex open set. Okay, what is the reason for convex open set? It's because the reason is when you look at the proof is that if this is convex set, now any 2 points we can find a path, right? Connecting, a segment connected. This is important because we use this property to construct an analytic function at capital. We use that to construct that. Okay. Without this property, it is very hard to construct an antiderivative. Very hard, okay? So, but for a simply connected domain, all right, for a simply connected domain, for example, the simply connected domain it is something like here. This is also simply connected. Okay, so this is also simply connected, but it's not convex. You can see that. So this open set is a simply connected domain, but it is not a convex set. Okay, it is not convex set. So that causes trouble when you want to define an anti-derivative. Right, you will have trouble. So for the simply connected domain, in general we don't have anti-derivative for F. Okay, but we still have this nice formula for any simple cross path gamma. Okay, so gamma is a simple cross path. Alright, now I will state, as I promised last time, that we can generalize the Cauchy's integral theorem to any open set. Okay? But we need something more. So it is not a proper place to put the so-called global Cauchy theorem. Okay, it's not a problem. Okay, so I just stop here. When you read through the textbook, the text always say something before it can be explained. Okay? Because the purpose of the textbook is just want you to have the ability to compute something. Okay. My job here is give you the logics, right? Why things is true. Okay. So even though I don't have enough time to give the proof in the lecture, but I try my best to give you the proof in the supplements. Okay, so this is the logical structure that you have. So you have at least you have these three versions of Cauchy's integral theorem are called local versions. Local, okay, local versions. So now I go to state the Cauchy's integral formula. They are very useful. Okay, and first of all, I have to introduce a concept called index. Okay. Now, so the gamma across the path. Oh, by the way, I think you have noticed the result in complex analysis, the defined domain, the defined play important roles. Okay, so we have to know what is the geometric property of the defined domain. So for here, sometimes we say that it's an open set. Sometimes we say it should be a domain. Okay. And sometimes we say it's complex open set, right? And sometimes here we say it's simply connected domain. So they describe the defined domain, the defined set, okay, the defined set we were talking about. Okay. And their geometry really matter, okay, in many important results. But of course, mathematicians, they want to generalize the result, right? Without any restriction. So for example, just say open set. Okay? And then there are no detailed structures for the open set. And then we can state a nice property, nice theorem on open set. Okay. So in the history, mathematicians usually search for such kind of generalized results. Now, we say gamma is a cross path, and the omega, the complement right? The complement of gamma star in the complex plane. I.e., omega actually is, right? So across space like this one, this is gamma star, right? So what is omega? Omega is what? Is here and also outside everything. This is omega, okay? So omega is the whole complex plane except a point on the cross spectrum. Except. So you have to see the relative situation, right? You have the gamma first. So gamma is the curved path, any curved space, right? And excluding the point on the cross path, all other points is an open set. Okay, it's called omega. Okay, so this is the situation. So now define okay, a complex function. A very special kind of complex function called index gamma. So the index function is relative to the cross path gamma. Okay? So it's defined to be 1 over 2 pi I, and we take the line integral over gamma, and 1 over psi minus z, and the d for all z in the open set. So the defining set of the index function is omega. Why the z can only be defined in omega? Because if z is a point on gamma star, when we do the line integral, because when you do the line integral, the psi, right, will go through the point on this path, right? And if z is on the curve on this path, then the difference comes to 0. Then you have to face with the 0 denominator, and that will be a great trouble. Okay? And often you don't know how to deal with that. So this index function can be defined at every point except the point, okay, on the path. So this is so we use the line integral to define it. Okay? And this function, which is called the index, okay, the index of point z in the open set with respect to what? With respect to the closed gamma. Okay? And what is the index of a point relative to a path, a cross path? Well, first of all, I give you the geometrical. So if a point z is here, for say z1, okay, and I have to give the orientation. So yeah, so the orientation is it's okay. So this is counterclockwise, right? I give the orientation, and the Z1 here, Z2 here. This is Z3, Z4, Z5. And I look at the relative situation of the point to the gamma star. Now I can write down what is the value of the index. Okay, so for here, I can write down the index. Now the index of gamma Z1 is equal to 1. Index of gamma Z2 is 0. Index gamma Z3 is 2. Index gamma Z4 2. Index gamma Z5 1. So what is 1, 2, 3, 4? They're always integer. Okay, for this case, all positive integer, impossible negative integer. So I will show to you that the index actually has integral values. Okay? And what is the exact geometrical meaning of the index? Is the so-called one number, the number of cycles, number of cycles when you go around through the. So suppose that you think about you have a pointer like here, and you go around, okay, through the path. And how many times you go? How many times you go one cycle? Okay, for Z1, you go here. So look at it here. The Z1, you are a person, right? You are a person. Look at and see the green dot. Okay, so suppose you are Z1, you sit here and see the green dot. You see, okay, it go around me, all right, and this way. Even though it go around here, but look to me, there's nothing, right? Just in this side. Alright, and so go this way. And up here, okay, just one round. Right? One round. So it's 1. How about when you see you are the person standing at Z2 and see the green dot, you will see that the green dot just do something, but just at this side, right? So the green dot does not around me anymore. It tried to around me, but then go back, right? You see here and go back and to here. So effectively, that the green dot does not around me for one cycle. No. So the value is 0. How about the third person this way? When you see here, you see that this one goes here, right, and up to here, right? Already one round, right? And then go to here, second round. So it go above these 3 for twice, 2 rounds. So the number is 2. The same is Z4. For Z5, the situation is like Z1, so it's 1. So the index, this definition, just give you the so-called 1E number. Okay, the 1E number of a point relative to a cross path. Right? And very interesting because it looks very complicated, right? A line integral, but the result is just an integer. Okay? It's always an integer. Right? So this is the geometrical definition. Okay, and from the value, so you can the whole compass plane can be divided into several components. For 1E number equal to 1, you see this component here. So this is one component. When in number equal to 2, you have this component or in this component. And the outside, so the gamma, the cross paths divide the whole complex frame into 4 components. Okay, into 4 components. And each one is simply connected. Okay, and every component has point in one component has the same Poynting number or the same index. You have the same index. Okay, so this is the geometrical meaning of this. Okay, and we will examine this definition and to see why we come up with the integral values. Okay, Thursday. Right? Any questions? Okay, so now, so I will see you.
为什么要在负10度左右？
对呀、
因为它那个 argument 那个角度那个曲子是从负拍到拍，
对呀、
所以它才切的。
那个负拍到拍那有弊，它为什么又把那个拍也给去掉了？
这个 branch count 那个概念是说，它是希望把一个，忘记。